This is Cameroon GCE A level chemistry 0715, section C, organic chemistry, June 2022, paper 2, question number 5. Fellow learners, a kind reminder for those of you who haven't subscribed to my channel. Please take some time now and subscribe to the channel so that my subsequent videos will come directly to you. Thank you very much for taking your time to subscribe to my channel. Let's get started. We are starting with June 2022, paper 2, that is organic chemistry, section 5. Question number 5. The question reads, A. Study the reaction scheme below and answer the questions which follow. Okay, you have a schematic diagram here. This is a schematic diagram that has been given, beginning from compound A, B, C, D, and D, E, and ending with compound F. There are a number of reactions here. So you should be versed with these schematic diagrams, what is required. Let's go straight to the question. Now, give the reagents and condition for step 1. Step 1, step 2, step 3, step 4, and step 5. Okay, as you know, step 1, step 1 is this is a hydrocarbon. This is a hydrocarbon that is being converted to 3, that is converted to a haloalkane. A hydrocarbon being converted to a haloalkane. It is really a substitution reaction. A free radical substitution reaction. So, 1, we are told, give the reagents and condition for step 1, step 2, and to right to step 5. Step 1, converting a hydrocarbon to a haloalkane. In that case, the one is bromopropane. That is bromopropane there. So to convert it to a haloalkane, it's a substitution reaction. And what type of substitution reaction is that one? It is since it takes place but under UV light, it is a free radical substitution. So now let's fill our answers. So now if you look at this one here, filling the answer, step 1, an alkane to a haloalkane or to a bromopropane. Step 1, a reagent in this case is supposed to be something like the reagent. The reagent here is bromine. The reagent is bromine. And the condition, since the conditions are under UV light, this is a free radical reaction, a free radical substitution reaction. So reagent are represented as arrow place. Reagent is bromine molecule. a reagent bromine molecule. Then condition. The condition is supposed to be under UV light. Under UV, uh, under UV light. But remember, note that this reaction, I just want to put here for the purpose of revision. For the purpose of revision, for the purpose of revision, it just for revision purpose, please. This for revision purpose is not in the included in the answer. It is a free radical. This is a free radical. A free radical substitution. It's a free radical substitution. So just for purpose of a revision purpose. So we have the reagent arrow is a bromine molecule and the condition is under UV light. Now let's go again. Let's proceed to the next number two. Number two. Okay, how can we convert? How can we convert a haloalkane? Now it is a haloalkane, and I'm seeing four carbon there. There is an increase in a carbon molecule, and there is an increase in a carbon molecule, and in order for you for a carbon molecule to have an increase in any organic reaction, an increase in because this is one of the special reaction where you don't have any carbon anywhere, but within a reaction there is an increase in a carbon atom. There is an increase in a carbon atom. Where you have nitrogen, and you see an increase in a carbon atom, know that that reaction is a nucleophilic substitution. There is a nucleophilic substitution reaction that is taking place, and using what we call a cyanide ion. Because the cyanide ion, the cyanide will give carbon and it will also give nitrogen. This is a nucleophilic substitution reaction with a cyanide ion when there's an increase in a carbon atom and a hydrogen there. So, what are the reagents in this reaction here? In the reaction here, the reagent we can see here, arrow. Let me go arrow to my as my reagent. Arrow is my reagent. Arrow here is what? Arrow is the reagent here is aqueous ethanol. There is aqueous ethanol as reagent. Aqueous, I say is aqueous ethanol. Aqueous ethanol in what? Yes, and potassium cyanide. There is aqueous ethanol. Then, and the potassium cyanide. Now, what are the conditions? C. Our condition C is this reaction. Our condition C is this reaction you must heat under reflux in aqueous ethanol. Heat under reflux. That is the condition. I said the condition here is heat this mixture under a reflux in aqueous ethanol. And for the purpose of revision, once more, I just want to attach here that for this reaction, we call this type of reaction where there is an increase in one carbon atom is called I say it's called nucleophilic substitution. Nucleophilic substitution with what? With cyanide ion. It's a nucleophilic substitution reaction with a cyanide ion. That is for the purpose of revision. Now, let's go to step three. Step number three. Step number three is how can you now convert this compound now because there's an increase there is an increase in a carbon atom using a cyanide ion. That is nucleophilic substitution reaction. What is going the compound that resolve like this one here? We call it a nitrile. We call it a nitrile. And how is this nitrile converted to a butanoic acid, into an acid? How are nitriles converted to acid? For nitriles to be converted to acid, we do what? We have to undergo acid hydrolysis. We have to undergo acid hydrolysis. That is hydrolysis in acidic medium. You hydrolyze the reaction in acidic medium. So now, what are the what are the reagent in this reaction? Reagent arrow. This is reagent arrow. Reagent arrow is reagent arrow in this reaction. I say the reagents. I say hydrolysis, acid hydrolysis. In this case, I am going to do aqueous acid. It could be hydrochloric acid. It could be sulfuric acid, but we'll call it acid hydrolysis. So aqueous, hydrochloric, or sulfuric acid. Aqueous aqueous acid. That is aqueous HCl, aqueous HCl, or sulfuric acid. Any of the two can go. So this is what we call acid hydrolysis. Let me attach it here. This is acid hydrolysis. Acid hydrolysis. This is acid hydrolysis for number three. So what is the condition? The condition here should be all this. You know that their conditions are always under reflux. You are hitting them under reflux. Condition. The condition here is heat with HCl or sulfuric acid under reflux. Heat with HCl or sulfuric acid under reflux. Yeah, heat with HCl or this under reflux. So it is an acid hydrolysis. Acid hydrolysis again, you can even another way of writing acid hydrolysis, you can say it is a two. You can say water is needed in the presence of an acid. That's the way they can write acid hydrolysis. Okay, let's go to number four. Number four is how can we convert a haloalkane like this one, bromopropane, to this is an alkene. This is ethene. How can we do this? Converting a bromopropane into an ethene molecule. So something has to be done. So in this case, it's going to undergo a certain type of reaction. Alcoholic, you are going to do it under alcoholic potassium hydroxide. That we are going to eliminate hydrogen bromide and some I think with water that will be eliminated too to give us an alkane, which is propene. So in this case, number four, condition for number four should be, I told you all most of these are under reflux. Here, what will be the reagent? The reagent will be for number four will be alcoholic potassium hydroxide. Alcoholic, alcoholic, alcoholic potassium hydroxide. Potassium hydroxide. Okay. Okay, let's move on to the condition. What are the condition? The condition. Just as I said a reagent in alcoholic potassium hydroxide, and the condition is that you have to heat under reflux. This is an elimination reaction. I I told you it's an elimination reaction in the formation of alkane. Alkane. So what should be our condition there? Our condition here is um excuse me. Heat under reflux. Heat under reflux. Yep. Heat under reflux. Heat under reflux. Remember, this is an elimination reaction. Elimination reaction. This is for the purpose of revision, please. It's not in our answer. Elimination reaction because a molecule because water is being released. Okay, let's go now to the last section. The last section is how can we convert the alkene, which is E, compound E is an alkene, which is propene, something like that. But I don't know the type of propene because it has many isomers the way I'm looking at it. So now how can we now convert this propene to bromo propane? Again, this is a bromopropane. So in order to react with an alkene, remember alkenes, they have a double bond. And in that double bond, in order to convert them into alkane, they will have to do what we call an addition reaction. Alkenes, we call them alkenes because they are short of, I think, two hydrogen atoms compared to the alkane. So in order to take them back to the group of alkanes, we have to add, there must be an addition reaction to fill that space. But this time around, it is not normal hydrogen, but what is there is a halogen, bromine. So there is an organic reaction involving double bond that will convert the double bond into a haloalkane. And that type of reaction is what we call electrophilic addition. Electrophilic addition on a double bond. There's an addition on a double bond to convert the alkane into an alkane. So what will be our reagent? Since bromine is involved, then something should be, it should be an HBr. If there were two bromine atoms there, we should have been talking of if there were two bromine molecules there, we should have been talking of something like electrophilic substitution. But since it is, we need to add to make up to alkane is an addition, and the only type of addition is electrophilic addition, and the only type of electrophilic addition is it involves a hydrogen bromide. So let's move on. So what should be our reagent here? Our reagent here, if you look at it critically, our reagent here is a hydrogen bromide that is required. A hydrogen bromide is required, HBr. HBr is required. Now, what about the condition? Our condition here, is that I said at room temperature. No, at room temperature. At they're doing the reaction at room temperature. But there's something you have to know. You have to keep in mind. What type of reaction involving hydrogen bromide at room temperature, converting an alkane to a haloalkane? We call it electrophilic addition for the purpose of revision. That's why I'm putting it on the side. We call it electrophilic addition. Electrophilic addition. Across a double bond. Okay, so we have five different reactions here. Free radical reaction, a free radical substitution reaction. There is nucleophilic substitution of the cyanide, which is number 2. There is acid hydrolysis, which is number 3. There is elimination reaction, which is number 4. And there is also electrophilic addition, which is number 5. Thank you. Let's move to the second part of our question. Give the structures of the compound D, E, and F. Of course, the structures from what I have, from what we have just discussed here, I have structures here for you, which I have converted them. These are the structures. Let me show you the structures. The structure for D. The structure for D is this. This is the structure we have for D. You know, D is an acid. We said it is an acid that D is an acid that is being formed. So that is D. Acid hydrolysis. We use that to form it. So D. This is the structure. D is butanoic acid. Butanoic acid. It has 1, 2, 3, 4. It's butanoic acid. This is the display structure. Now, you go. What is the structure for E? If you look at E, which I said the structure was an alkene, I saw it is a propene. This is a propene. 1, 2, 3. And because there are 3 carbon there and a double bond, we call it an alkene, which is propene. And if we want to use the IUPAC system of naming it, we will say this is the first carbon. This is the first carbon here. I call it, this is the first carbon. Let me say this is the let me put it like that. This is the first carbon. This is the second carbon. And this is the third carbon. And I can name using the first carbon by saying that it is prop 1. Prop is the prefix, prop 1, prop, then the first carbon that the double bond is attached there. Then what is the homologous name is alkene. So we end with a suffix in. The prefix is prop, then the position is the first carbon, which is 1, and the suffix is in. Prop 1 in. That is according to the IUPAC system. Now, compound number, the other compound. This is compound F. Compound F is, this is compound F. Compound F. This is F according to this. Compound F. Compound F. If you look at compound F from here, from this structure here, you will see that compound F, F, it was converted to, I say it was 2-bromopropane after the conversion of this alkene through, after the conversion of this alkene through electrophilic addition of hydrogen bromide. So we had this compound here, and we can name it as, we look at it following the IUPAC system of nomenclature. We have, this is from here to this place is the same. From here to this other place is the same. We can either name from either 1, 2, and 3, or you could start naming from here 1 or 2 and 3. What you have noticed that it falls on the same second carbon. So therefore, we give the name as 2-bromo. Then the parent chain is what? 1, 2, 3. That is the parent chain, which is the longest chain, is 1, 2, 3, and that is propane. So that is the structure number F, display structure of F. So now let's go to, we are done with the structure A, D, E, and F. Let's get back on board and start with, we are done with the structures of D, E, and F. They are there. Now let's go to question number 3. Outline the mechanism for the reaction of compound E. This is compound E. I told you compound E is what? Is an alkene, which is a propene. And now outline the mechanism for the reaction of E with what? With bromine water. That is bromine in tetrachloromethane. Okay, the mechanism, you have to outline. When they say outline is, when you say outline, you are just listing the steps. It doesn't have to go with description. Okay, just briefly, maybe like a sentence. You can say the first sentence. You can say like now, what is here? You can say the first sentence, step 1. You can say step 1. That's the outline. Let me come. The outline is like a procedure. Step 1. You outline it. This takes place, this happened like this and that. 2. Follow this, it will result in this and that. 4. 3. Will cause this and that. 4. There's a formation of this and that. 5. There is this and that. And that's just how they want you to do it. Okay, I have a sample here for you. Outline the mechanism of the reaction. Let me show you. You don't have to, for the purpose of revision, that's why I have written this. But what you need to do is step number 1. I said it is electrophilic addition of propane. Mechanism for the reaction of the compound E with bromine in tetrachloromethane. That is the mechanism. Step number 1. This is step number 1. Step number 1. The bromine molecule approaches the carbon-carbon double bond. That is the molecule. That's the first step. The bromine molecule approaches the alkene molecule. That's the first step. Just state it like that. Outline number 2. Step number 2. A dipole is formed. Full stop. You can state another thing there. You can say a dipole is formed. You can now brief the dipole to be. You can brief the dipole to be bromine bond. That's a dipole. A dipole is formed. So what you need to do here is that for the purpose of explanation, I said just state a dipole is formed. That's all. And then you can state this molecule here. And then you can state the molecule like this. Bromine having a partial positive, 2 double bonds, then with other bromine, negative bond. That's a dipole that is being formed. These are 2 poles. So what is happening here is this, for the purpose of revision. As the bromine molecule gets closer to the double bond of the alkene, what happens? The pi bond in the double bond repel the bonding electrons. The bonding electrons, electron pair in the bromine molecule, thus inducing a dipole. I have said I've said, how is the dipole formed? As the bromine molecule gets closer to the double bond in the alkane, the pi bond in the double bond will repel the bonding electron in the what? In the bromine molecule, thus inducing what? Inducing a dipole. It induces a dipole. This is how it is. Step number 3. What you need to still do in step number 3 is heterolytic fission in the carbon-carbon bond, in the bromine-bromine bond. Full stop. Heterolytic fission. Heterolytic fission. It means the division is unequal. The breaking of the bond is unequal. Heterolytic fission in the bromine-bromine bond. How does this occur? This result in one of the, you can now say this result in one of the bromine atoms taking all the bonding electrons. Full stop. This is what happens. Heterolytic fission in the bromine bond. What happens is that here, because of the repulsion, because of the double bond, as the bromine molecule approaches the double bond in the alkene, there are double bonds there. The double bonds are full electrons. Electrons are negatively charged, and the bond here, they have electrons. The bond between the two atoms of bromine, they have electrons. No, electrons are negatively charged, so like charges will repel. So the electron, the bonds in the double bond in propene will push or will repel these bonding electrons here towards one of the bromine. You see the electron coming toward one. They are supposed to be in the middle, but you see the electrons are moving, but towards one of the bromine. It comes to a point that there's what we call heterolytic fission. Hetero means unequal division, unequal breakage. It comes to a point that this one will break, and this other bromine will go with a double bond, and this one will be left with nothing. So this one will have a plus charge, and you have a negative charge with the electron, and we call them cation and anion. That is step number 3. Step number 4 in this type of reaction. What happens in step number 4? Electrophilic attack. This one, that is, this one you see like this, which is this one that you see like this, which is positively charged, or that has more electron. You see, the one that is positively charged, it needs electron, because all the electrons that were sharing has been taken by one. In that case, we will call this a cation, which is, we will be acting as an electrophile. What are electrophiles? Your teacher must have told you that electrophiles, these are electron deficient species. These are atoms. These are ions or species that don't have enough electrons. They are electron deficient. They lack electrons to make up the 8 electrons in their outermost shell. So for that reason, they are very, very reactive. Once more, electrophiles are electron deficient species. These are electron pair acceptors. They will also accept a pair of electrons. They are electron deficient species, and they are ready to accept a pair of electrons to complete their octet of electrons. In that case, we now say number 4. What will happen there? Electrophilic attack. This one is going to go on attack. So now, so the double bond has excess of electrons, both the pi electrons and the sigma electrons. Because of the pi electrons that are there, we now say that the double bond is rich in electrons. For that reason, this one is attracted towards the double bond. So we call it electrophilic attack in organic chemistry. So the bromine ion, now electrophilic attack, which is number 4. You can now explain. The bromine ion, which we call the cation, act as an electrophile by doing what? By accepting a pair of electrons. By accepting a pair of electrons. They will act as an electrophile by accepting a pair of electrons. by accepting a pair of electrons from the pi bond. And this will lead to what? This will lead to the formation of an unstable carbocation. It will lead to which will lead to the formation of an unstable carbocation. Then let's go to number 5. Number 5 is the carbocation. A carbocation bromine anion bond formation. There is a carbocation and a bromine ion bond formation. That's the last stage. Here, the other bromine molecule, which is this one that has 2 lone pair of electrons. A carbocation. What do I mean by a carbocation? Is a carbon atom that also lacks electrons. They have incomplete electrons. So in that case, they have a positive charge, and will require a pair of electrons to complete their octet too. So this one will be acting. Bromine will be acting to fill that place. So in that case, a carbocation bromine anion bond formation. The other bromine anion, which is the anion, forms a covalent bond with the carbocation, with the unstable carbocation, by donating a pair of electrons to it. That's good. These are the stages you are supposed to write. Write just briefly. I was writing it for the purpose of explanation to you. But what I have told you are the underlying area that you just have to state in your during exams. Now, you might be confused. What are pi bonds? For the purpose of revision, you might be confused. What are pi bonds? If you have a double bond like this one, the double bond is made up of what? The pi bond and the sigma bond. Okay, this is a model. This is a model here. This model here, this is a carbon with hydrogen. Let's say this is an ethene molecule. So this ethene molecule, the central bond between the 2 carbon atoms, we call it the sigma bond. This is the sigma sign. Then along overall the molecule, the whole molecule is now covered with what? With the pi bonds. It's the same thing that is happening in a molecule of benzene. So there are pi bonds here that are moving around here. We call this place a high cloud of electrons. There's high density of electron here because of these pi bonds. So pi bonds, the high cloud of electrons, we call them the pi bonds, plus the sigma bond is what is giving us the double bond here. So when an electron deficient species like an electrophile is attacking this double bond here, it wants to get 2 bonds from here because this place is full of electrons. That's why it always go on electrophilic addition. Thank you. Let's go get back to the question section. You now see the different steps, the outline that I have given you here. Let's go now to B. Suggest chemical tests which could be carried out to distinguish between the following pairs of compounds. You have here we have, if you look at the functional groups, you see that it is an aldehyde functional group. Here there is an aldehyde functional group. But if you look at their carbon atoms, this one is an alkyl group, which we say it is 1, 2, 3. There are 3 of them. Aldehyde, let me say there are 2. Yeah, this is an alkyl group. Then this is an aryl group. This is an aromatic compound. This is an aryl group and this is an alkyl group. Between these two, there's an alkyl benzene. There is an aldehyde group attached to a benzene ring. An aldehyde group attached to a benzene ring. Any aldehyde group that is attached to a benzene ring, if you look at it, any aldehyde group attached to a benzene ring, you will see that any aldehyde group that is attached to a benzene ring, you will see that there is the name is benzaldehyde. Is benzaldehyde. because it has an aldehyde group attached to the benzyl ring. On the other hand, this other one is an alkyl group attached to the aldehyde group. And here we have 1, 2, 3, 4, 1, 2, 3. So we call it propanol. So in this way, how can you separate what chemical test is used to dictate aldehydes? And in this case, aldehyde of different functional aldehyde of different side chains. The major functional group that is used in the dictation of aldehyde is what we call the tolerance reagent. A tolerance reagent or tolerance test. A tolerance reagent or a tolerance test. Okay, I have something here for you. It will help you understand this better, which is this one. Here we have this. You have, I say it's propanol and benzaldehyde. That is an aldehyde group attached to the benzyl ring, and this other one alkyl group to the aldehyde group. We use a tolerance test or a tolerance reagent. So what I will say is that because we have a one unique test that we use in this one, we can now say that when they say, how can you do this? The way you can place it is that when propanol is added to tolerance reagent in a test tube, that's how you are supposed to explain it. But if limited marks are given, you can just state it as I've stated it here. So when propanol is added to a tolerance reagent in a test tube, the silver ions are reduced to metallic silver. The silver ion there are reduced to metallic silver. The equation is there, forming a silver mirror on the test tube walls. So in this case, forming a silver mirror when this substance propanol is added into tolerance reagent in a test tube, what is going to happen is that there is a reduction in metallic. The silver ions are reduced to metallic silver, and what happens? There is the formation of a silver mirror on the walls of the test tube. That's what you will see here. On the other hand, these are the observations. On the other hand, with this aromatic compound, which is benzaldehyde, you can say, you know that this one here, because of a high the resonance here, because of the resonance here, this ring here stabilizes. This ring here stabilizes the benzyl ring. That ring here stabilizes the molecule, and the compounds react to achieve stability. Compounds react to achieve stability. If a compound does not react very fast, it means that it's stable. So in this case, there is stability here, and for that reason, this compound is less reactive. There's a reduction in the reactivity of this compound. For that purpose, we can say, because of the reduced reactivity of the benzyl aldehyde, due to what? The stability of the ring. Because of the reduced reactivity of the benzyl aldehyde by the resonance stabilization of the ring, it produces what? Less distinct silver mirror and a red-brown precipitate of cuprous oxide. So the resonance, because of the resonance stability of the ring, this one is less reactive. And what happens? There's a formation of silver mirror, quite right, but it is less distinct. Formation of less distinct silver mirror and a red-brown precipitate of cuprous oxide is formed in this benzaldehyde. So that is the difference between the two aldehydes. That's the difference between aldehyde formed from an aromatic compound and aldehyde formed from an alkyl compound. So now that is the difference. You can write shortly like that, then you are okay. Formation of silver mirror on a silver mirror on the test tube, on the walls of the test tube. Formation of less distinct silver mirror and a red-brown precipitate of cuprous oxide. That's the main thing. Let's go. The second one is what? The second one, according to the this thing, is between. There are two compounds that were given. Two compounds were given, which are the two compounds are this is an alkyl group. Alkynes. These are all alkynes. They have triple bonds. They are all alkynes and they have triple bonds. And most learners will be wondering how this compound has a double bond, has a triple bond, this one has a triple bond. How am I going to be differentiating them? It was even better here because this one was an aromatic compound. This one is an alkyl, compound. It has an alkyl group. But this one, they are the same. But let me tell you something. It has to do with the reactivity. It's the reactivity and the type of product that result that's going to differentiate them. Let me show you something. Okay, let's move again on what I prepared for you on this other section. Okay, taking into consideration these two compounds. The two compounds are what we call, they are all alkynes. They contain triple bonds. But according to the IUPAC system of naming, this compound is named as the first. This is the first carbon. This is the second. This is the third. This is the fourth. So because the triple bond is on the first carbon here, we say it is 1-butyne. Okay, come here. We have 1, 2, 3, 4. If we name from here, will be 1, 2, and 1, 2, 3, and 4. If we name from here, we'll see 1, 2, 3, and 4. So the compound is, the double bond is either attaching it to the second position this way or the second position this way. In that case, we name it as 2-butyne. But how can we differentiate these compounds? With a chemical test. And the chemical test we can differentiate this compound is partial hydrogenation reaction test. A partial hydrogenation reaction test. Now, there's partial hydrogenation because we don't convert all the compound directly to alkanes. We converted just one reaction. That was a partial. If it was full hydrogenation, it is right to alkane. But it is partial because it's only one time that we are converting it, just from alkyne to alkanes. So the first one in butane 1, the test is partial hydrogenation reaction test. So reacting 1-butyne, reacting 1-butyne and 2-butyne with 1 mole of hydrogen will produce alkanes. That's the only thing. Reacting 1-butyne and 2-butyne, 1-butyne here and 2-butyne here with 1 mole of hydrogen, that is a hydrogen molecule, is going to produce alkane. 1-butyne will produce a terminal alkane. This is a terminal alkane. The terminal alkane, where an alkane is attached to the first carbon atom. While 2-butyne will produce an internal alkane. An internal alkane is that the double bond is in between. Once more, the test we can use to differentiate alkynes, this the alkyne, is by reacting, that is partial hydrogen reaction test, to produce what we call partial hydrogenation reaction test. So I said reacting 1-butyne and 2-butyne with 1 mole of hydrogen will produce alkanes. And the differences are these. 1-butyne will produce a terminal alkane. This is the terminal alkane here. 1-butyne, when you react with hydrogen, you see what? The hydrogen are added here. More hydrogen are added here. More of the hydrogen will be added here and here. One of the hydrogen is added here, and one of the hydrogen is added here. So it now becomes this one and this one. And if we want to name it according to the IUPAC system, this is the first carbon, this is the second carbon, the third carbon, the fourth carbon. So the double bond is located on the first carbon. And the parent chain, how many carbon atoms are there? The longer chain, 1, 2, 3, 4. We now say but is our prefix. Then the second, the position of the carbon atom is 1. But 1. Then our prefix is what? In. But 1 in. That is a terminal alkane produced by partial hydrogenation reaction. That's the one test to differentiate this. On the other hand, we have 2-butane. On the other hand, we have 2-butane. 2-butane using the partial hydrogenation reaction. When we react 2-butane with hydrogen, it's going to produce what? It's going to produce what we call an internal alkene. Internal due to what? The different position of the triple bond. And internal alkene is what? Hydrogen is going to be added here. There's one, okay, hydrogen is added to this one hydrogen here. One hydrogen is added here, and one hydrogen is added here. So one bond is cancelled out. Only the double bond is left. One hydrogen is here, one hydrogen here. It kicks off this one bond here. So only the double bond is left. And this is the structure. This structure here, when this double bond goes, when this bond goes off, this becomes the bond. Okay, the hydrogen is here, hydrogen is here. This is the hydrogen here, this is the hydrogen. This is the methyl group. Now it is now forming a cis compound. The methyl groups are located on the same site. So it's now going to form. It has given us what? It has given us an internal alkene. Internal alkene is what? The double bond is in between, is the same, is located in the middle. 2 carbon this way, 2 carbon this way. And in naming this compound, we call it what? This is the first carbon, this is the second carbon, this is the third carbon here, this is the fourth carbon. And what is the parent name? Is but. That's for butane. But. Now, since the alkyl groups, or what we call the methyl groups, are located on the same side, we say it is a cis isomer. And in that case, it will be cis but, which is our prefix, the second position, which is but 2, and our prefix is in. We have cis but 2 in. That is how it is. It's not trans. It has produced but a cis isomer. So that is it. That's how you can differentiate this. Thank you very much for that. Thank you. Thank you. Let's move on to the other question. I just realized that along the line, I think we missed a question. We missed a question in the course of trying to. We missed number 3. We missed. There's a question we missed here. There is a question we really missed. I think there is a question here, which is how this compound is being formed. For the purpose of revision, I will get back to it. Don't worry. Don't worry. So we are on. We have differentiated these 2 compounds. We are on C. Question number C says, organic chemistry is the chemistry of mostly carbon-containing compound. State 2 unique properties. State 2 unique properties. State 2 unique properties. State 2 unique properties of carbon. That's good. Carbon is unique in chemistry. Because the whole of organic chemistry is taken away by the carbon element. So what are the 2 unique properties of carbon? I'm going to give you a list of about 4 unique properties of carbon. You cannot choose from those 4. Carbon here, we can say carbon has the ability to catenate. Catenation You can say one, catenation. You can say two, catenation, variety of bonding. Okay, variety of bonding. You can say three, allotropy. Allotropy. That is another unique property of carbon. And number four, you can say tetravalency. Tetravalency. So carbon has four unique properties. We call them catenation, ability to catenate, variety, formation of variety of bonds, allotropy, and tetravalency. So let's start with catenation. Carbon will carbon's ability to form long stable chains and ring by bonding with itself is what we call catenation. That is the ability of carbon to form long stable chains and rings by bonding with itself is what we call catenation, and that is what makes carbon unique. That property makes carbon unique. The second one, variety of bonding. The ability of carbon to form single, double, and triple bonds with itself and other atoms makes carbon a unique element. The third one is allotropy. Carbon exists in different forms. Carbon exists as diamond, carbon exists as graphite, and carbon exists as fullerenes. That's another form of carbon that makes carbon unique. Then the last one is tetravalency. Carbon has it has 4 valence electrons. Carbon has 4 valence electrons in its atom shell that enable it to form 4 covalent bonds with other atoms. I say it has 4 valence electrons in the atom shell that enable it to form 4 covalent bonds with other atoms. Now, those are, you can choose from the two to give from these two from the 4 that I've given and choose 2 from there. So I was going to go to the to one thing for the purpose of revision for those of you who will be, because you'll be writing in a few months from now. Outline the mechanism for the reaction of compound E with bromine in tetrachloromethane. Yes, you may have the mechanism like as outlined here. You may have the mechanism as outlined here, but there's something that is lacking. You could be given the molecules and asked to write the steps. Or another thing with the examiners are very trickish. They could write the equation, they could write the mechanism down and omit some certain steps for you. And if you understand these steps, how the mechanism is going, you could easily fill those spaces. So one thing you should know how to write to follow this procedure here to write the equation in the mechanism. For instance, this mechanism here is given here. Let me explain how it works in this equation here. For this reaction here, this is what was formed. They said we were not told how carbon. I mean, the mechanism for the reaction of this with what? With this compound E. With this compound. See, this is the mechanism. How bromine? This is bromine. I want to explain the mechanism to you now, please. There were 4 stages. I mean, 5 steps. I want to show you how it reacts, even though we are not asked for the purpose of revision. This is the molecule that we're given. This E, propene. Now it is reacting with bromine in tetrachloromethane, CCl4. I told you the first step is one, carbon. I said the first step is excuse me. The molecule approaches the carbon-carbon double bond. This molecule here, when bromine molecule is approaching this carbon-carbon double bond, as I told you, the first step is this molecule approaches this one. That was first step number 1 I gave you. Step number 2, I said, as I said, there's a dipole that is formed in step number 2, which I said, as the bromine molecule get closer to the double bond, the pi bond in the double bond repel the bonding electrons in the bromine molecule, and what? Inducing a dipole. I told you that when this molecule comes closer here, what happens? There's a pi bond here. I explained that earlier. This pi bond, because of the because they are negatively charged, and the electrons, these electrons here are negatively charged, there is repulsion. See this approach. The repulsion between these electrons here and the electrons in the pi bond. And what happens is that because of the high density of electrons here, these one are having a heavy force. They will push this one this way. And when they push this, they are pushing it to the other bromine molecule, inducing what? A dipole. When they push electrons here, we now say their electrons are concentrated this way, and this place is lack of electron, and that's why we give it a partial positive charge, because it is deficient of electron, and this one a negative charge because it has high density of electron this time around. Step number 3, I told you there's heterolytic fission. What happens is that you may not see it here. What happens is that when it comes here, there's a breakage of this bond, and this one goes without electron, and this one will go with this lone pair of electron. Now, step number 4 is electrophilic attack. The electrophilic attack is now what? This cation here that is deficient of an electron is acting as an electrophile, and is going to attack this high rich carbon here. It's going to attack this high rich carbon here. It's going to attack from this end. This end that is going to attack. It's going to attack from this from here. It's attacking here. Sorry, it's attacking here. As it's attacking here, because it is attacking what? It is deficient of electron. It needs electron. It is short of electron, so it need to make its atom share 8. So it needs 2 pair of electrons from these pi bonds here, because there are many electrons here. Will now attack this and gain electrons from will now accept a pair of electrons from this pi bond here. By doing that, it's going to form a bond, a covalent bond with this carbon, and that's what you find here. Step number 5, the last step is what? This is what you find here. And when it forms a bond here by accepting a lone pair of electrons, it means only one bond is left. There's no more double bond. When it adds itself here, no more double bond. It's only a single bond. But in the course of doing like that, it causes a carbon atom that is also deficient of electron. And this carbon atom that needs more electrons to complete its 8 electrons will do what we call it a carbocation, because 1, it lacks electron. 2, it is highly reactive to get electron from, by all means, to fill up its outer shell. So by doing that, this other anion that split from the other bromine and is having a lone pair of electron is happy to do what? To donate the electron here. So it does that by doing what? Donating a lone pair of electron to this active or very reactive a carbocation. And a full bond is now formed between a carbon and another bromine. And that leads to what? To this molecule here. And that leads to this molecule. And that's the molecule that is being formed. By doing like that, we now say the molecule is what? All atoms, by reacting, they have gained a full state of electron. And how do we name the molecule? This is carbon 1, this is carbon 2, and this is carbon 3. And by doing like that, we start from 1. How? Because of the different groups that are there, the bromine groups that are there. We say 1, 2. There are 2 bromines there. We say 1, 2 di, because there are 2 of them. Dibromo. What is the parent name? 1, 2, 3 is a propane. So 1, 2 dibromopropane is the name of this molecule. So that is it. If you can do this, study your mechanism very well, the way I've explained to you, fellow learners, I am certain you are going to make it. My goal to you in your exam is that you should understand the basic concept in chemistry, so that challenges ahead, you'll be able to handle them and become good future engineers, future pharmacy students, future medical doctors, future aerospace engineers, future environmentalists, future educators, and any field you desire to be. Thank you. Bye-bye.